Hello, welcome. In the first part of this lecture, we discussed convergence of a sequence. In this part, we are going to talk about bounded sequences and prove some theorems relating the convergent sequences and bounded sequences. Let's begin our discussion with the definition of bounded sequence. A sequence in R is said to be bounded if there exists a positive real number m such that the absolute value of p sub n is smaller or up to equal to m for all n. In other words, a sequence in R is bounded if there exists a positive real number m such that p sub n is larger or equal to negative m, but smaller and up to equal to positive m for all n in n. For example, the sequence 1 over n in R is bounded since for all n in the set of natural numbers, we have the absolute value of 1 over n is smaller or up to equal to 2. Here 2 is m. So there exists a positive real number m, for example 2, such that the absolute value of all the terms is smaller or up to equal to the m. The following figure clarifies this argument. If we plot first few terms of the sequence, for example, the first term, the second term, the third term of the sequence in a two-dimensional plane, we see there exists some real number m, 2, such that all the terms are lying in between two straight lines defined by the equations y equals 2 and y equals negative 2. To prove this, we use the fact that n is greater or equal to 1/2, since n is a natural number. So the absolute value of p sub n is equal to 1 over n, which is clearly smaller or equal to 2, following from this inequality. And this statement is true for all natural number. Hence, the sequence 1 over n is bounded. Notice the real number m is not unique. If the statement is true for m equals 2, it is certainly true for any m value larger than or equal to 2. For example, m could be 3 or even greater values. Question: does every bounded sequence converge? No. Let's have a look at the following example. In the earlier part of this lecture, we proved that this sequence is a divergent sequence. However, it is a bounded sequence. Let's see the proof. If we denote the terms of this sequence as p sub n, then we observe that P sub n equals 2 if n is an odd positive integer, or P sub n equals 0 if n is an even positive integer. Therefore, clearly, the absolute value of P sub n is smaller or equal to 2 for all n in the set of natural numbers. The following figure shows the fact we proved. Let's have a look at another example. The sequence in R is unbounded. Let's see the proof. Let's define P sub n equals to n times 1 minus negative 1 to the n. Now, as previous, we observe that P sub n equals 2n if n is an odd positive integer, and P sub n equals 0 if n is an even positive integer. For example, P sub 3 would be 3 times 1 minus negative 1 cubed, which is 6. On the other hand, P sub 4 equals 4 times 1 minus negative 1 to the 4, which gives 0. Therefore, clearly, there does not exist any m such that the absolute value of P sub n is smaller or up to equal to m for all n in the set of natural numbers. Because if such an m exists, then by Archimedean property, there would exist a positive integer n such that 2n is greater than m. Now, if n is odd, then P sub n equals 2n, falling from the definition, which is greater than m. On the other hand, if n is even, then n plus 1 is an odd positive integer, and we have P sub n plus 1 equals 2 times n plus 1, which is surely greater than 2n. Which is greater than m. So in either case, there exist terms in the sequence which would cross or exceed m for every m. For example, if we take m as 2, we see that there exists some term goes beyond or higher than m. If we assume m equals, for example, 6 or example 10, there would exist some term would go beyond 10 or even higher values. So clearly, this sequence is an unbounded sequence. Theorem. If a sequence P sub n converges in R, then its limit is unique. Every convergent sequence in R is bounded. So the contrapositive statement of the statement B is if P sub n is unbounded, then it is not convergent. So this statement says any unbounded sequence must be a divergent sequence. Let's have a look at the proof of these statements. Suppose there exist P and Q real numbers with P not equals to Q such that the limit of P sub n as n grows to infinity equals P, and the limit of P sub n as n goes to infinity is also equal to Q. We want to show that P must be equal to Q. So since our hypothesis is that P is not equals to Q, we would lead to a contradiction. Take epsilon equals the absolute value of P minus Q over 2. By hypothesis, epsilon is now positive since P and Q are not equal. Then for this choice of epsilon, there would exist positive integers n sub 1 and n sub 2 such that the absolute value of P sub n minus P would be smaller than absolute value of P minus Q over 2. Since the sequence P sub n is a convergent sequence, so for every epsilon, there would exist some positive integer. So for this choice of epsilon, there would exist some positive integer. Similarly, since Q is also the limit of the sequence, then the absolute value of P sub n minus Q would be smaller than the absolute value of P minus Q over 2. For all n greater than or equal to some other integer n2. Now we define a positive integer n as shown. It is the maximum of n1 or n2. Then from the triangle inequality, we have the absolute value of P minus Q is smaller or equal to the absolute value of P sub n minus P plus the absolute value of P sub n minus Q. But since this quantity here is smaller than the absolute value of P minus Q over 2, similarly, this quantity is also the smaller than the quantity. So their sum would be smaller than the sum, which is the absolute value of P minus Q. Hence, we proved that the absolute value of P minus Q is strictly smaller than the absolute value of P minus Q, the same quantity, for all n greater than or equal to n. But this is clearly false. So this contradiction proves that our initial hypothesis was wrong and proves that P equals Q. Let's have a look at the proof of the statement B. Namely, every convergent sequence is bounded. Let P sub n be a convergent sequence in R that converges to some real number, P. Now we take epsilon equals to 1. Then for this choice of epsilon, there would exist a positive integer n such that the absolute value of P sub n minus P is smaller than 1 for all indices n larger or greater than n. Now we define M as follows. This is the maximum of the absolute value of the first term of the sequence, the absolute value of the second term, and all the way up to the absolute value of n minus 1 term of the sequence, and 1 plus absolute value of P. Then we claim that the absolute value of P sub n is smaller or equal to this positive quantity M for all n in the set of natural numbers. Because by the definition of M, the absolute value of P sub 1 is smaller or equal to M, since M is the maximum of all these quantities, or P sub 2, the absolute value of P sub 2 is smaller or equal to M, and all the way up to the absolute value of P sub n minus 1 is smaller or equal to M. And for all n greater or equal to n, we have, by the triangle inequality, that the absolute value of P sub n is smaller or equal to the absolute value of P sub n minus P plus the absolute value of P. But this quantity is strictly smaller than 1, and this quantity stays the same. Therefore, the absolute value of P sub n is strictly smaller than the quantity 1 plus the absolute value of P. But this quantity is smaller or equal to M, since M is the maximum of this quantities. Therefore, we proved that there exists some positive real number M such that the absolute value of P sub n is smaller or equal to M for all indices in the set of natural numbers. Hence, every convergent sequence is a bounded sequence. This concludes the proof. The statement A of this theorem, namely the uniqueness of a limit of a sequence, was proved by the method of proof by contradiction. To see a direct proof of that statement, please consult the lecture note.